Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're continuing our lecture on electrochemistry, and we've made it to the second objective. In the second objective, we want to cover cell potentials, which help us determine which electrode species will be oxidized and which will be reduced in an electrochemical cell. The relative tendencies of different chemical species to be reduced have been determined experimentally using the tendency of hydrogen ion to be reduced as an arbitrary zero reference point. Now, the first thing we want to talk about is reduction potentials. A reduction potential is measured in volts, and it's defined relative to the standard hydrogen electrode, She. That is what that acronym stands for, standard hydrogen electrode. This is conventionally given a potential of 0 volts. The reduction potential of a species is going to indicate its tendency to gain electrons and be reduced. Each species has its own intrinsic reduction potential. The more positive the potential, the greater the tendency for that species to be reduced. Now, we could also talk about standard reduction potential. This is measured under standard conditions, so 298 Kelvin, 1 atmosphere pressure, and 1 molar concentrations for all of the reactants and products. These standard conditions allow us to compare the relative reactivities of different half cells and then predict the direction of electron flow. A more positive standard reduction potential means a greater relative tendency for reduction to occur, while a less positive or more negative standard reduction potential indicates a greater tendency for oxidation to occur. Now, in a galvanic cell, which operates spontaneously, the electrode with the most positive reduction potential acts as the cathode, where reduction occurs, and the electrode with the less positive reduction potential acts as the anode, where oxidation occurs. Since the species with the stronger tendency to gain electrons actually does so, the reaction is spontaneous, and the change in Gibbs free energy, delta G, is negative. In an electrolytic cell, which requires an external power source to drive a non-spontaneous reaction, the electrode with the more positive reduction potential is forced to act as the anode, where oxidation occurs, by the external voltage source. The electrode with the less positive reduction potential is then forced to be the cathode, where reduction occurs. And since the movement of electrons is against the natural tendencies of the electrochemical species, the reaction is non-spontaneous and delta G is positive. It is important to note that reduction and oxidation are opposite processes. To obtain the oxidation potential of a given half reaction, you have to reverse the reduction half reaction and then change the sign of the reduction potential. Now, something else we want to talk about is the electromotive force, also known as EMF. The electromotive force of a reaction, also known as the standard electromotive force, this is the difference in potential and voltage between two half cells under standard conditions, and it is calculated using the standard reduction potentials of the two half cells involved in the reaction. It's given by the following equation. Now, when you're calculating the EMF, you're going to subtract the reduction potential of the anode from the reduction potential of the cathode. And it's crucial not to multiply the standard potentials by the number of moles oxidized or reduced, because the potentials of each electrode is independent of the amount of material. It depends solely on the identity of the material. That is so important. I'm going to repeat it once more. It's crucial, it's important not to multiply the standard potentials by the number of moles oxidized or reduced, because the potential of each electrode is independent of the amount of material, and it depends only on the identity of the material. The standard reduction potential of an electrode will not change unless the chemical identity of that electrode changes. With that in mind, we can go ahead and move into our last and final objective. Here we're going to discuss the electromotive force and thermodynamics. Throughout our discussion of electrochemistry and the different types of electrochemical cells, we've been making references to the spontaneity or non-spontaneity of the redox reactions that are housed in each of the different cell types. Let's now look more formally at this topic by relating free energy to electromotive force and the concentration of the redox reactants and products to the voltage of a cell at a given point in time. We're going to start with Gibbs free energy. The electromotive force, the EMF of an electrochemical cell, is a measure of the voltage that's generated by the cell. This voltage arises from the difference in the reduction potentials of the two half cells. Thermodynamically, the EMF is related to the Gibbs free energy change of the electrochemical reaction. For electrochemical cells, the relationship between Gibbs free energy change and EMF is given by this equation, where delta G is the standard change in free energy, N is the number of moles of electrons that are exchanged, F is the Faraday constant, and this term right here, E cell, is the standard EMF of the cell. Keep in mind, if the Faraday constant is expressed in coulombs, then delta G must be expressed in joules and not kilojoules. Now also note the significance of this negative sign right here. All right, this negative sign on the right side of the equation. Delta G and E cell will always have opposite signs then. Therefore, galvanic cells have negative delta G and positive E cell values, and electrolytic cells have positive delta G and negative E cell values. Now, the best way to learn how to use this equation is obviously by tackling a practice problem. This example says determine the standard change in free energy of a cell with the following net reaction, and here is our net reaction. We're also given that the standard reduction potential of iron 3 is positive 0.77 volts, and the standard reduction potential of molecular chlorine is positive 1.36 volts. Now, the first thing that we want to do is we want to separate the reaction into the half reactions. So here they are. In this reaction, iron 3 is reduced and it is the cathode, whereas our chloride ions are oxidized and it is the anode. Now, the reduction potential of chlorine is actually higher than that of iron 3. And so this means that the electrodes are serving the opposite role from their natural tendency. And this reaction is non-spontaneous. So if this is non-spontaneous, this is an electrolytic cell and it should have a negative EMF value. Now we can go ahead and calculate that EMF value. It's going to be equal to 0.77 volts minus 1.36 volts, and that gives us negative 0.59 volts. Now that we have this calculated, we can use the EMF to determine the free energy change. Note that there are two electrons that are transferred. So in our equation, N is going to be equal to 2. F, this is Faraday's constant, and we just calculated the EMF. So we can go ahead and plug things in here. We have negative 2 moles of electrons multiplied by Faraday's constant, which is 96,485 coulombs per mole of electrons, and then that's multiplied by the EMF we calculated. What we get is going to be 1.14 times 10 to the 5th power joules. The free energy change is about 114 kilojoules, which represents a non-spontaneous reaction. Wonderful, so that's how we attempt this example problem. Now, the next thing we want to talk about is the Nernst equation. The Nernst equation is a crucial tool for understanding how the electromotive force, the EMF of an electrochemical cell, changes with varying conditions, particularly when the concentrations of the ionic species deviate from the standard state of 1 molar. Now, the standard equation for the EMF of a cell assumes standard conditions like we discussed earlier, 298 Kelvin, 1 atmosphere pressure, and 1 molar concentrations for all of the reactants and products. However, real-world applications often involve conditions that differ from these standards. And so the Nernst equation accounts for these deviations, and it provides a way to calculate the EMF under non-standard conditions. That equation looks something like this, where E cell is the EMF of the cell under non-standard conditions, E not cell is the EMF of the cell under standard conditions, R is the ideal gas constant, T is temperature, N is the number of moles of electrons, and F is Faraday's constant. And here we also have the natural logarithm of Q, where Q is the reaction quotient for the reaction at a given point in time. Now, the following simplified version of the equation can also be used assuming T, temperature, is equal to 298 Kelvin. So this is a version of that equation when the temperature is equal to 298 Kelvin. Now, the simplified version of the equation, it essentially brings together R, which is the ideal constant, the ideal gas constant, and T, which is temperature, we're assuming 298 Kelvin to get this simplification, and F, which is Faraday's constant, and we convert the natural logarithm to the base 10 logarithm to make calculations easier. Now, just as a friendly reminder, remember that the reaction quotient for a general reaction is equal to the concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. Now, keeping that in mind, let's go ahead and tackle this practice problem. This example says find the EMF of a galvanic cell at 25 degrees Celsius based on the following standard reduction potentials, and in this cell the concentration of iron 2 plus is equal to 0.01 molar, and the concentration of chloride ions is equal to 0.1 molar. Now, the first thing we need to do is determine the standard cell potential. Because the chlorine half reaction has a higher reduction potential, it's going to be the cathode. Iron is going to act as the anode, and the standard cell potential can be calculated like so. We have 1.36 volts minus negative 0.44 volts, and this gives us a total of 1.8 volts. Now we want to determine the net ionic equation. Remember here that iron is being oxidized, so its reduction half reaction in the question stem is going to have to be reversed, and it will give us the following net ionic equation. Now from here, we can actually determine the value of the reaction quotient. Remember, Q is equal to the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. And remember, we don't include solids or liquids. So Q is just going to equal the concentration of iron 2 plus multiplied by the concentration of chloride ions raised to 2 because that is its stoichiometric coefficient. Essentially, we're just multiplying 0.01 molar by 0.1 squared molar, and that's going to give us 10 to the minus 4. Now we can go ahead and plug it into the Nernst equation, keeping in mind that 2 electrons are transferred, so N equals 2, and we're operating here under the assumption that temperature is at 25 degrees Celsius, which is equal to 298 Kelvin, so we can actually use the simplified version of the Nernst equation that we just talked about in this form. All we have to do now is plug in values. So this is going to be 1.8 minus 0.0592 divided by 2, and then log of 10 to the minus 4. This is going to give us a total of 1.92 volts, and that is the answer for this example problem. Now, the next thing we want to talk about is how we can re-express the standard free energy change. In a previous chapter in this playlist, we defined the standard free energy change to equal minus RT natural log of KEQ, where R is the ideal gas constant, T is the absolute temperature, and KEQ is the equilibrium constant for the reaction. In this chapter, we define the standard free energy change to be equal to minus NF E naught cell, where N is the number of moles of electrons exchanged, F is the Faraday constant, and E naught cell is the standard EMF of the cell. So now we have two definitions for the standard free energy change. We can go ahead and set these equal to each other. And when we do, we get the following expression. Now here, this is going to be really important because we can now express a relationship between the cell potential, between the EMF, and between the equilibrium constant. Now we can say that when KEQ is greater than 1, E naught cell is positive. And when KEQ is less than 1, E naught cell is negative. And when KEQ is equal to 1, then E naught cell is 0. So this equation provides a direct link between the spontaneity of an electrochemical reaction, the cell potential, and the position of equilibrium. Now, knowing the effects of concentration on equilibria, we can now derive the change in Gibbs free energy of an electrochemical cell with varying concentrations using this equation, where delta G is the free energy change under non-standard conditions, delta G naught is the free energy change under standard conditions, and R is the ideal constant, T is the temperature, Q is the reaction quotient. With that, we can move into our last and final topic for this lecture, and that is on electrochemical stoichiometry. Electrochemical stoichiometry connects the concepts of charge, current, and time to the quantitative aspects of electrochemical reactions. To begin, let's define electrical current. Current is defined as the rate of flow of electric charge through a conductor. Mathematically, it's expressed as I is equal to Q divided by T. I represents the current measured in amperes. Q is the total charge measured in coulombs. And T is the time over which the charge flows, and it's measured in seconds. From this definition, we see that current is a rate. It's specifically the amount of charge flowing per unit time. So for example, 1 ampere of current corresponds to 1 coulomb of charge passing through a conductor every second. So we can say that 1 ampere is equal to 1 coulomb per second. Next, we have the Faraday constant. This provides the link between electric charge and the number of electrons involved in a reaction. The Faraday constant represents the total charge carried by 1 mole of electrons, and it is approximately equal to 96,485 coulombs per 1 mole of electrons. This value is essential for calculating the amount of chemical change driven by a specific electric current over time. It tells us that transferring 1 mole of electrons through a circuit corresponds to a total charge of 96,485 coulombs. So to summarize, the two key concepts to take away are 1, current is a rate. It describes how much charge flows per second through a conductor. And 2, the Faraday constant bridges the gap between charge in coulombs and the quantity of electrons in moles, and that allows us to calculate the relationship between electrical input and chemical output in electrochemical systems. With that being said, let's jump into a practice problem. This problem says, what mass of copper will be plated out when an aqueous solution of copper sulfate is electrolyzed for 20 minutes with a constant current of 25 amperes. We learned in General Chemistry 1 that chemical stoichiometry involves using mole-to-mole ratios from balanced chemical equations to determine quantities involved in chemical reactions. That means that in electrochemical stoichiometry, we must always begin with a balanced equation. However, the equation we need is not the overall balanced equation. Instead, it's the half reaction, which indicates how many moles of electrons are transferred per mole of reactant or product. In this equation, copper is being plated out of a solution of copper sulfate. The oxidation state of copper in copper sulfate is +2, so the relevant half reaction is copper 2 plus in aqueous solution plus 2 electrons. This gives us solid copper. Now that we have the balanced equation, we want to keep in mind that every electrochemical stoichiometry problem can be solved by focusing on two important relationships. The first is the definition of electric current, and that is I is equal to Q divided by T. And the second relationship is that the charge of 1 mole of electrons is equal to 96,485 coulombs. So we can go ahead and write these down to keep them in mind as we solve the problem. Now, the first step we want to do is we actually want to figure out the charge transferred. So that means we're going to take advantage of this equation right here. We are given current, that's equal to 25 amperes, and we're given time, 20 minutes. So we can rearrange this equation to solve for charge. Charge is equal to current multiplied by time. So let's go ahead and plug these in. Current is equal to 25 amperes. Now remember, amperes is 1 coulomb per second. Keep that in mind because this is going to be important in the way that we're going to represent our time. We're given time in minutes, but we want to convert that to seconds so that our units of seconds cancel out and we get charge in units of coulomb. So we have 20 minutes. We're going to convert that to seconds. We know that in 1 minute, we have 60 seconds. So then if we plug this into a calculator, we get that Q is equal to 3 times 10 to the 4 coulombs. Perfect. Now that we've determined the amount of charge transferred, we can use Faraday's constant, which is the charge of 1 mole of electrons, to calculate how much copper plated out. So we're going to write down our goal. Our goal is to figure out the grams of copper. To do this, we're going to begin the calculation with the number of coulombs of charge transferred, which we just determined is equal to 3 times 10 to the 4 coulombs. Then we want to use Faraday's constant to convert from charge to moles of electron transferred. For 1 mole of electrons, we have 96,485 coulombs. Then our next step is perhaps the most important step of this calculation. We're going to use a mole-to-mole ratio. Let's look at our half reaction here. Copper was reduced from copper 2 plus to solid copper, so every mole of copper that plated out required 2 moles of electrons. So for 1 mole of copper, we had 2 moles of electrons. Then from here, we can go ahead and convert the moles of copper to mass using the molar mass of copper. For 1 mole of copper, we have 63.55 grams of copper. So notice here, coulombs cancel out, moles of electrons cancel out, moles of copper cancel out, and we're going to get our final answer in units of grams of copper. If we plug this into a calculator, we're going to get that we have 9.88 grams of copper that plated out. And with that, We've solved this problem, and we have finished our final lecture. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.